hopefully by like tonight, and we'll send it in Discord.
Cool. Okay, so let's just run through this one more time real quick.
So as we learned last week, a reference frame is just a point of view in which motion is measured, which is often, a abstract coordinate system. Time is measured in seconds, denoted by the letter T, and is a scalar. Position is a scalar denoted by the letter X and is the location relative to the reference frame. Distance is the path of motion denoted by the letter D, measured in meters and is a scalar. Displacement is a vector denoted by delta X, measured in meters, and is the distance from start to finish. Speed is the total distance divided by the total time, is denoted by the letter S, measured in meters per second, or m divided by s, and is a scalar. Velocity is displacement divided by total time, denoted by v, measured in meters per second, and is a vector. Acceleration, denoted by the letter a, is a vector defined as velocity divided by total time and is measured in meters per second squared.
So once again, the equations that we're going to be focused on this week are the kinematic equations. And a lot of this slideshow and this section of our time together is going to be predominantly just plugging and chugging numbers in an equation to find out other parts of the system. So the first one is that final velocity is equal to the initial velocity plus acceleration times time. And this equation is derived from the acceleration equation, which, as you can see here, and we mentioned earlier, is just acceleration equals the change of velocity divided by time. And as you can see, that plays out perfectly in this equation. The next equation is that final x position, or final position, is equal to the initial position plus initial velocity times time plus the half of the acceleration times time squared. And this is one of the more complex equations, and that is because it's derived through calculus and also has a lot more complex algebra derivation. And if you want to learn more about that, you can definitely check it out. It is very interesting, but not part of the AP Physics 1 curriculum, so we're not going to worry about it. And the third equation is that the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times the change of x. And this equation is found by plugging in the first equation into the second equation. So most of these equations are very interrelated to many of the themes that we've been discussing earlier and within each other. So if you ever get stuck, you can obviously try to work backwards and try to derive them other than really the second equation. Oh, someone's here. And all of these equations can be found on the equation sheet, which is going to be part of the AP Physics exam, and we'll be sharing it with you later on because that's basically, you don't need to memorize any of these equations. It can be found right there. So we're just going to play this short video. It's around 6 minutes, and it's just going to show an example of working through a problem so you can get used to how it's set up and how to work through it, basically.
Number 3. A motorcycle speeds up from 24 to 60 meters per second and travels a distance of 500 meters within that period. What is the average acceleration, and how long did it take to reach a speed of 60 meters per second? So let's make a list of all the variables we have. The initial speed is 24 meters per second. The final speed is 60 meters per second. The distance is 500 meters, and our goal is to find the average acceleration initially. So what equation has v initial, v final, a, and d? The equation that we need is this one. V final squared is equal to v initial squared plus 2ad. So v final is 60, v initial is 24, and We don't have the value of a, but d is 500. 60 squared, that's 60 times 60, that's 3,600. 24 squared is 576. And 2 times 500 is 1,000. Let's subtract both sides by 576. So 3,600 minus 576, that's 3,024. Now, if we divide both sides by 1,000, 3,024 divided by 1,000 is 3.024. So that's the acceleration of the motorcycle. You could round it to 3 if you want to.
Oh, you did. Okay, so that's basically the process in which is most recommended for people. Of course, your process can be however you prefer, but most people, at least I personally prefer to write down all of the variables that are given to us in the equation. For example, the initial velocity, the distance traveled, and the final velocity was also the second part of the question. And that way, you know which variables you have and also which variables you want to solve for. And with that process in mind, you can choose the proper equation to help you solve for what you need to. And that just makes sure that everything is organized and you're not basically racing against the clock. So now we're going to talk about a more specific application to these kinematic equations, which is when an object is thrown up and when it's thrown down. So in these scenarios, there are very specific characteristics that will help us solve the kinematic equations. For example, the velocity and the acceleration. So the velocity is always positive if it's going up and negative if it's coming down. And that makes sense because it's basically a direction. And with that in mind, there has to be that one point when the velocity is 0. That split second is the maximum point. So in a curve, you should throw something up and down. When it hits that maximum point, it slows down. And I'm sure you guys can visualize that when you throw like a ball across a field or something like that. And at the very peak, it looks like it's stopping for that very split second, and that's what we're talking about. And this situation can be attributed to the constant acceleration, which is negative 9.8 meters per second squared. And this occurs because it's the acceleration due to Earth's gravity. And we're going to go more in depth of how that's derived in later units. But for now, all that you need to know is that it exists, and a lot of times we round it to negative 10. And that the lowercase letter g is the constant that we use for 9.8. So when we derive the maximum height and total time, we use these laws and these characteristics of this type of motion to help us solve for a constant truth that occurs in any of these motions that are like this. So for maximum height, we know that at the top of this motion, the velocity is 0. Therefore, the final velocity of the situation is 0. And when we solve for the change of x, plugging in the final velocity is 0, we get that the change of x is equal to negative initial velocity squared divided by 2 times acceleration. And as I mentioned earlier, a lot of times we replace negative a for g. And that helps simplify the equation and also remind us that it is a constant. And for the total time, the logic behind this is that throughout the entire curve, halfway would be half the time. And halfway is when we reach our maximum point. So therefore, if we solve for the amount of time it takes to reach our maximum point and multiply it by 2, we can get the total time. So when it's thrown up, we get that the final velocity is 0. So then we can solve for t, which equals negative 2 initial velocity divided by the acceleration. And again, like before, replacing negative a with g, and we get 2 times the initial velocity divided by g. A lot of times we don't actually use this memorized formula in our head during the AP exam because it's not given on the equation sheet. And as you can tell, it's literally derived from these formulas. But it's very important to understand that this occurs and that it's a constant throughout any motion that occurs like this, where the acceleration is constant and at g.
And so we're going to compare that to objects that are just simply dropped. So right now, Tanvi just described what happens if you throw a ball in the air. Now we're considering what if you just drop a ball? You don't throw it down, you just drop it. And so in that scenario, we have free fall. And in that case, in free fall, we only have one force, and that's the force of gravity pulling the ball down. And we'll get to forces in a couple of weeks, but right now, we just need to notice that in AP Physics 1, we don't deal with any kind of friction, it's just gravity that's pulling the ball down. And so, as Tanvi mentioned, we also have an acceleration because of this gravity, and that's negative 9.8 meters per second squared. So basically, gravity is pulling the ball down by negative 9.8 meters per second every second. And so there's three types of motion of free fall. The first one is that you kind of drop the ball down from let's say you have a tall building and you drop a ball down. In that case, acceleration is negative 9.8 meters per second. We have the force of gravity pulling it down. And the initial velocity is 0. If you throw it down, the only thing that happens is that the initial velocity now changes, right? If you throw it, now the initial velocity is, for example, minus 25 meters per second. And as Tanvi just described, we also just recently covered the scenario in which an object is thrown straight up and comes down. And you can see in all three scenarios, acceleration is minus 9.8 meters per second squared. And there's also a few other fun facts kind of that you can always derive, but sometimes it's useful to know that the time it takes for a ball to come up will be the same as the time it takes to come down. And the velocity at any point on the way up will be the same as the velocity on the way down. So for example, if I throw a ball up at 25 meters per second squared, it'll come back into my hand at 25 meters per second squared. And finally, at the top of its arc, the ball will be momentarily still, so we say its velocity is 0. So that's a lot of information, which we kind of threw at you. So the best way to get to know this is to practice. And so I'm going to turn it to Mark, who's going to go through our first practice problem.
I would just like to point out that you were saying 25 meters per second squared instead of 25 meters per second.
Yeah, sorry about that. Should have been meters per second.
Okay.
Also, before we go on, do you guys have any questions? Because as Keshav said, that was a lot of information. Okay, if not, we can go into the practice problems and get more used to this sort of skills.
All right. We have a car traveling at 30 meters per second and uniformly decelerates for 50 meters until it comes to a stop before the traffic lights. What is the uniform deceleration, and how much time does it take for the car to stop? We'll give you maybe a couple minutes to see if you can figure this out on your own, and then we'll come back to you then.
And we know this is the first problem and that you haven't really given any practice yet. So it's okay if you don't get this one right off the bat. Hopefully by, the sixth problem or the fifth problem, it'll kind of become easier.
Do you guys have the equations written down, or would you like us to go back and then? Okay, I'm just gonna assume that you guys have it, but feel free to let us know if you don't have it, and then we can always go back to the slides to take a quick note.
Yeah, private message us the answers you got, and once everyone's done that, we'll go over the problem.
Or you can just text us that you weren't able to solve it, and that's fine.
All right, I'm going to start explaining now. The first thing we see, is that, well, this is v naught, because that's the starting velocity. And so we'll put v naught equals 30 meters per second. And that v final, since we're told it comes to a stop, is going to be equal to 0 meters per second. And this is going to be equal to delta x. Okay, so I've been told that we can use the text feature. We see that v final square, the proper formula to use is v final squared equals v initial squared plus 2ax. Then we can isolate a to get a equals v final
Mark, are you
squared.
writing somewhere? Because I don't think we can see it.
Oh, you can't see it?
No.
I was typing. Here, I'll switch to writing then.
Maybe you should click away. Oh, okay. Maybe it's just me then.
Okay.
Sorry about that.
So we get vf squared minus v initial
I can't see it either. Unless...
squared. Palin, can you see it? Okay. I'll switch to drawing then. We have vf squared equals vi squared plus 2a delta x. Sorry for my messy handwriting. We can simplify this, or well, isolate. We can isolate a to become a equals vf squared minus vi squared over 2 delta x. Plugging our formulas in, or plugging our values in, we get negative 900 divided by 100. So we have negative 9 meters per second squared. Because 900 is in meters squared per second squared divided by meters. We can just cancel out one of the m's and we're left with meters per second squared. And now I'm going to erase all of that so that we have space for the next one. And now there's no good way of erasing other than just this, which is kind of silly. Let's do it this way. Can you guys see my writing?
Yes.
Okay, interesting. So, as we found, we had -9 for this. -9 meters per second squared. And that is really messy. For the next one, we're going to use, now that we have this, we can just use VF. No, Grace, it shouldn't be 9 meters per second squared because we're slowing down. And since we're slowing down, it's always going to be, we're taking 9 meters off of our speed every second.
I mean, I think maybe you could have 9 meters per second squared if you consider deceleration with a
Oh, that's
negative
true.
sign.
That's true. Since it's deceleration, it's positive. But usually in physics, we don't really use the word deceleration,
Yeah,
in
I
my
think,
experience.
yeah.
We just say the acceleration is negative.
So for this problem, it might be acceptable, but I think usually, yeah, it's a better habit to put -9.
Yeah. So with our next formula, we have, or for our next problem, we can use VF equals VI plus AT. And the reason why is because now we have acceleration and both velocities. So because VF is 0, we could just say negative VI equals negative, or is equal to AT, or T equals negative VI over A. So we have negative 30 meters per second divided by negative 9 meters per second squared. And this is going to give us 3.33 seconds. Is that clear for everyone?
Okay. I'm gonna move on to the next one.
Okay, I'll clear my,
Okay. There we go.
all right.
So for the next problem, we have a ball dropped from a tall building and it hits the ground 4 seconds later. So again, we have two parts. First, how tall was the building? And second, what was the ball's velocity just before hitting the ground? So I'll go ahead and give maybe 4 minutes so we can check back at 12:48. So I'll go ahead and start this problem now. This is actually a classic physics problem, and maybe some of you have seen, even Mark Rober actually made a video on this. I'll just go ahead and put it in the chat for anyone who's interested. It's a really cool video where he basically just talks about this problem in real life to measure the height of a cliff. And so for this problem, let me just see if I can get the annotate tool working. So for this problem, we know only a few things. We know that the initial velocity, can you guys see my text? Or
No, unfortunately not.
You'll just have to write.
Oh, it came up.
It came
okay.
up.
Okay, cool. So we know the initial velocity is 0 meters per second because it's dropped, and we know that the total time it takes is 4 seconds. And so if that's all we know, you can actually still use this equation over here, x equals x naught plus v naught t. Yeah, I think you can only see it once I kind of click out of the box. So once I'm typing, you can't see it, yeah. And the reason why we can use this equation is because we don't really actually need this initial position. We can say it's just 0. We know the initial velocity, and the acceleration due to gravity in AP Physics 1 problems is pretty much always minus 9.8 meters per second squared because gravity is pulling it down. And so if you just read this, now we have a quadratic equation where we have 1/2 AT squared plus V 0t plus x naught minus x equals 0. You can kind of see, you guys see this? This is a quadratic equation where we have t kind of as your usual x, and we have we usually have ax squared plus bx plus c. In this scenario, 1/2 a would be your a, v naught would be your b, and x naught minus x would be your c. Or you could just go ahead and plug the numbers directly in the second step here. And if you just plug in these numbers, you'll notice that this is a little weird. 1/2 times minus 9.8 squared is equal. So yeah, if we just kind of plug in the numbers, what we really actually want to solve for here was x minus x naught, sorry, not the t, because we're looking for the height of the building. So in fact, what we had, the second equation was actually fine. Sorry about that. So if you just plug in the numbers, you have x is equal to, the initial height is 0 plus v0 is 0 plus 1/2 at squared. So that's just 1/2 times 9.8 times the time squared is 4 squared, which is 1/2 times 9.8 times 16. So hopefully you got 78.4 meters per second. Let me just, I think I already have, yeah. Let me just put it in the chat if it helps. Kind of like that. So that's how you get 78.4 meters. And you might notice that x minus x naught turns out to be minus, but that's because if you start from the top and jump to the bottom, you're actually kind of traveling a negative distance. You're going from the top to the bottom, which is why you have a negative answer. So when we talk about the height of the building, we usually want a positive answer, which is why it's 78.4 meters. And next question is, what was the ball's velocity right before hitting the ground? And so now that we know the height of the building, we can use a different equation. You can kind of see here that we know the initial velocity is 0. We want to find the final velocity. We know the acceleration due to gravity is minus 9.8 meters per second squared. And we know the height of the building now is 78.4 meters per second squared. Sorry, 78.4 meters. And so if you just solve for the final velocity here and plug in the numbers, you get 39.2 meters per second.
Is everyone good with that one? Okay. So we're running really close to the end of our class, but I'm just gonna do a quicker run through this question because it is really classic physics. Okay, sure. Could you just, yeah. It is a very classic physics problem where they ask you to draw the position time graph, velocity time graph, and the acceleration versus time graph. So this is a very similar problem to what we were talking about earlier, where a ball is thrown straight down from a very tall building. And then try to draw these while just thinking about how the ball should be moving, so qualitatively. And I'll give you a minute or two, and then we'll go quick through this so we have time for questions.
Is it just me or?
Yeah, she's breaking up for me too.
Yeah, okay, it might be my Wi-Fi. Can you guys hear me now?
No, not really.
Yeah, I
Okay.
think you're still frozen as well. It's like a parabola, right? Kind of goes like this and then back, right? So um, that's what the position versus time graph really ends up looking like. Since we're throwing it straight down, however, in this scenario, it's just going to fall straight off the building. It doesn't have a chance to go up. So we only actually have the second kind of half of for the velocity versus time part is 0. And the acceleration versus time will always be minus 9.8 meters per second squared. And so this is a classic problem they kind of like to give on the AP Physics exam. What happens if you drop a ball from a tall building? Position will kind of look like a parabola. Velocity will be straight down, and acceleration will be flat. Sorry, Tom, do you want to do the next one? Or
I just don't think we have time for it. If you guys have any questions,
frozen again? Oh, okay.
Yeah. Do you guys have any questions though? We can definitely talk about something else to fill the time. Feel free to put them in the chat box if you don't want to say it aloud.
We will be sharing the other questions on Google Classroom also. We have like a couple others planned out, so maybe you could take a look at them also. Hope you find them helpful. And we'll see if we can fix the Google Classroom issue. Is it working for you, Tanvi? Because I know I'm signed up as a teacher also, and it's kind of working for me, but I'm not sure. If you try to join now, the join code doesn't work anymore.
Oh, okay. Let me check. Is it the same code or did I type it in wrong?
It's possible that you typed it in wrong. I'll check the code.
But in the meantime, if not questions, do you guys have any feedback for us? That would be really helpful. If not,
Here,
you guys.
I'll put the code in the Zoom chat. See if if it works for you guys. If it does, then we should be fine.
It works? Oh, okay, it works. That's great. So we can put that into the Discord. Anyways.
Yeah, you forgot a letter in your.
Yeah, you forgot the number 6, which is why it kind of errored.
Oh, got it. Okay. Sorry about that, guys. Typo.
Yeah, so you'll want to change that in the physics class message.
Mm-hmm. I'll add that in.
And does anyone have any questions? Because otherwise we can stop the recording and say bye.
Okay, I'll stop the recording then.